I think there was an issue with the message. Apparently it did not go on time, so that's why we don't have a lot of people here today. But anyway, today we're going to do the example I promised we will do from chapter 30, and then we'll tackle chapter 31, unless you guys have any questions. So let me share with you the screen. What is it? Okay, so from chapter 30, as I promised, we have an example from problem 59. And problem 59, I copied it already from the publisher's basically a book that they provided. So in the circuit shown in this figure, okay, switch S is closed at time t equal to 0. With no charge initially on the capacitor. Initial conditions are very, very important from now on because of the fact that they impact a lot the answers that you are going to get. Most of the times, at least for this class, we'll start with no charges or no currents, and sometimes with none of both of them, they're not there, okay? So in this case, what they're saying in here is at t equal to 0, when we switch the circuit, there is no current. At t equal to 0, I is equal to 0. I'm sorry, did they say I equal to 0? They said Q equal to 0. I'm going to assume that I also is equal to 0. In the circuit, so no charge initially on the capacitor. So there is no charge on this capacitor, okay? Find the reading of each ammeter and voltmeter just after the switch is closed. So once the switch is closed, once you throw it all in the closed position, basically, current starts to come from the EMF, the 40 volt EMF, and goes through the resistor, the 50 ohm. Now, because of this inductor, it has the potential across it is proportional to basically the rate at which the current is changing. It doesn't like the current to change at all. So it's going to oppose that. So initially, this will be an open circuit in here, okay? So the current cannot go through an open circuit. It's like you don't have anything. So this is how so far the circuit would look like immediately after you switch you put the switch on. So the switch now is closed. So you have the resistor of the 50 ohms. And in here, it's an open circuit. Then you have the other resistor of the 100 ohms. Now, when you hit this point in here, at that point, the capacitor has no charge, so it's going to allow as much current to flow through it to charge it. So this looks like it's actually a wire in here, okay? Since it's a wire, all the current will flow in here, so it's going to shortcut basically the resistor in here. So there will be no current going through this, as if this resistor doesn't exist at all in the circuit, okay? So all the current that flies through the 50 ohms, remember this is a 40 volt, will not go through the inductor because it's basically an open circuit. And then we'll go all of it because this is short-circuited now, basically, because of the capacitor will act that basically is going to have no charge in here. So the voltmeter V5 will read 0. That we know for sure. The voltmeter V5 will read 0. Okay, and the V2 in this case will read infinite. It's going to be open. So V2 will read infinite. It's basically you're just putting it in front of in the air, okay? A2 will read 0 because there is no current flow going through this ammeter. Since A2 is 0, I can find the voltage in here 0 times the 100, so V3 also will be 0. So V3 will be 0, V2 will be 0, and I'm sorry, it will be infinite in here, okay? But the current A2 will read 0. Okay, this current A4 will read whatever current is flying in here. The voltage V5 will be 0 because there is no component in here. There is no charge in the capacitor. So V5 will be 0. Now, since the voltage V4 actually will also be 0 because there is nothing in here, between these ends, okay? But the current in here, there is no current A3. A3 will be infinite, will be 0, I'm sorry. There is no current that is going to go through A3. And V4 is going to also be 0. So all of these readings are just immediately after the switch on. So if you turn it on, that's what's going to happen. Now, the circuit again, so the current, let me get more real estate. So the current now is going to come from the other end and basically close the circuit. So whatever current I is going to encounter only a resistor of 50 ohms and come straight through back to the battery. So basically the current that is going to be here is going to be 40 over 50 or 4 over 5, which is 0.8 amps. So the reading on A4 and the reading on A1 will be 0.8. So A1 and A4 will both of them read 0.8 amps. Okay. How much V1 is going to read? V1 is going to read actually 0.8 times 50, which is going to be 40 volts. So V1 is going to read the entire EMF that is actually in the battery. The entire voltage that is in the battery coming from the battery. Because that's the only component at the end of the day. This is how the circuit looks like immediately after you throw the switch in the on position. This is as simple as it can get. So basically you have a 40 volt in here, which is the same 40 volt in here, and the current, which is going to be 0.8 amps. That's it. That's basically how you throw when you throw the circuit on, because the capacitor will short circuit the circuit in here, and this will be an open circuit immediately after. So that answers the first question. So we got all of the ammeter and the voltmeter. Find the reading of each meter after a long time has elapsed. So now after a long time has elapsed, the capacitor is fully charged, and it's going to break the current. The current cannot go through the capacitor when it's fully charged. You cannot run current. You cannot build more chargers on it since it's fully charged. So when you wait too long, then this will be open in here. So V5 will be infinite and A4 will be 0. This one, when it's fully charged, the current will be steady, so the voltage V2 will become 0. Because remember, L di over dt, when you wait a long time, it's going to fully charge and the current will be steady. So di over dt, the derivative of a constant, is 0. So V2 will be 0. So there will be a current now, A2, that I need to find. And there will be V3 that is just the product of this current times the 100 that's I need to find in here. Now, there is a current in here, which is A1. There is a voltage in here, which is V1, that we need to find. This one will be open because now the capacitor is fully charged. It's not going to allow current to go through. So this will be 0 after a long time, okay? So whatever current that is going to come in here has to go through V4, has to go through the 50 ohms, basically. So this is, if I wait a long time, this is how the circuit look like. Now I have still my battery in here. I have my 100 ohm. I mean, what is it? This one, is it 50 ohms? Sorry. Okay. Now this will be a wire replaced by a wire. The inductor will be replaced by a wire. I have the 100 ohms in here. There will be an open circuit in here for the capacitor because it's fully charged, so nothing will flow through it. So I'm going to leave it alone because it's open. Basically, you don't have anything. And now you have the 50 ohms. And again, this is how the circuit looks like after a long time. So now, basically, the current that is going to come in here is going to split in here. This is 50 ohms. Is it 50 or? Yeah, it's 50 ohms. So now, I have to just find the R equivalent for the entire circuit. R equivalent for the entire circuit, we have two resistors in parallel and one resistor in series with them. So the R equivalent will be just the sum of the two resistors, which is 50 ohms, plus the inverse of the sum of the inverses. Okay, this will be simply equal to 50 times 100 divided by 50 plus 100 plus 50. So this is the entire R equivalent of the circuit at this point. Remember, I have a 40 volts in here for the EMF. So that should give me the value for the current that is going to run through the first 50 ohms. So in this case, what is this algebra in here? So I have 150, 5,000 divided by 150 plus 50. So I have 5,000 divided by 150. So it's going to be 33.3 basically ohms plus 50. So it's going to be 83.3 ohms. 83 and a third of an ohm. Okay, so that is the entire R equivalent. So that gives me I1. I1 is going to be the 40 volt divided by 83 and a third. Okay, or 83.33 if you like. So that's going to be an ohm in here. So the current is going to be a little less than half an amp. Half an amp. So it's going to be what? 40 divided by, open parentheses, 83 and a third. It's going to be 0.48 amps. Okay, so it's going to be 0.48 amps. That is the current that is running through the first 50 ohms and read by A1. So A1 will be a little less than half an amp, which is actually 0.48 amp. So that's how much A1 will read. Now, if you ask me how much voltage is in this 50 ohms, it's going to be 50 times this current because it's the same current. So this will be 50 times 0.48 amps. So this will be, let me get the calculator quickly, 0.48 amps, 0.48 amps times 50. So it's going to be 24 volts. So 24 volts is read by this voltmeter, which may leave me with a voltage, because if I do 40 minus 24, that is what, 16 volts? 16 volts must be read by this voltmeter. So there is a 16 volt, because 16 plus, no, not this diagram, I'm sorry, the one in the bar. This is the ohms, yeah. 16 volts is here and 24 volts in here. By the way, 16 volts is also here too, because these are in parallel, they have the same voltage. So there is a 16 volt in here or 16 volt in here, whichever way you like it. So I have 16 volt in here. How much current is running through this one? It's 16 divided by 100. So it's going to be 0.16 amps read by A2, the emitter in here. So this will be 0.16 amps. If you're curious trying to find how much current now is running through A3, A3 should be then just the difference between 0.48 amps and 0.16 amps. So it should read 0.24 amps. Let's check it. Let's see if I do the 16 volt divided by 50, that should be the same thing. So I remember I have a 16 volt in here. That's my argument, because it's the difference between the 40 volt and the 24 volt. That should be 16 volt divided by 50 ohms. That should read 0.24 amps. So I have 0.24 amps, and on this side I have 0.16 amps. They should add up to the total current that is read by A1, which is 0.48 amps. Okay? So I have all the voltages. V5 is going to be infinite in this case because it's an open circuit. Okay, A4 is going to be 0 in the second case because there is no current flying through that area because it's an open. And V2 will be 0 because di over dt is 0. It's steady current now, so V2 is 0. A2 turned out to be 0.16 amps, and V3 is going to be equal to 16 volts because 0.16 times 100 is actually 16 volts. And in here, 50 times 0.24 is actually 16 volts. So both these sides, because they're in parallel, they have the same voltage. This is no longer implicated in the circuit because it's broken. Basically, it's an open circuit. Okay. So after a long time, that is how much the devices will read. So initially, when I have thrown the whole thing on, the A1 will read actually after I turn the switch on, because in this case, this will be a straight wire, and this will be open. So in that case, V2 will be infinite, A2 will be 0, and V3 will be 0, and V5 will be 0, and A4 will be equal to A1, and A1 and A4 will be 0.8 amps. That's immediately after we close it. V4 will be 0, because A3 also will be 0. There is no current that is going to go through here. After we wait a long time, the current in A1 drops to 0.48 amps from initially 0.8 amps. And the current in this one will be 0.16 amps. The voltage V2 will be 0. The voltage V3 will be 16 volts. The voltage in V4 will be actually 16 volts also. And the current A3 will be 0.24 amps. The voltage V5 will be infinite, will be open basically. And the current A4 will be 0. And the current and the voltage in here will be just 24 volts. So 24 plus 16 volts is exactly the initial voltage, which is 40 volts. Does this problem make sense to you guys? Because this is really at the heart of a lot of homework problems and understanding of what's going on in these circuits. Does it make sense to you guys? Or did I go too fast on it? I think practicing will help a lot. Let me tell you what this whole class is about. It's not about circuits, by the way. In which case, V2 is infinite in when? Initially or after a long time? Let me check. Because this class is just an introduction to circuits, really. So when you get into circuits, you're going to deal with far more examples than this. So let me go back into the example to exactly where is V2 first. V2, initially, you want to run a current through the inductor. The current doesn't like to change the current, okay? So it's going to act as if it's going to oppose a current, as if the wire, the plug in your household that's open basically. When you put a wire in them, it's going to short circuit it. But when it's open, the plug, like any plug. Oh man, no, that's what I do. Sorry, I have to put this in its place. What is it here? Anyway, the point being in here is, it's like this basically. You have two wires sitting in front of one another. That's why the current doesn't go through them, because it's a dI over dt. The whole point of the mass, for example, doesn't like to change its velocity. So if you try to push it, initially it's going to resist. That is the point. Okay. Ultimately, V2 is not going to stay infinite. It's going to drop to 0 at the end of the day. What happened here? Okay. For some reason, everything went blank on me. You guys understand? So the whole thing in here, it's going to start to build the current in it. As it starts to build the current, now the voltage starts to change in it until at some point drops to 0. Because at that point, there is no more changes in the current because dI over dt becomes 0. The same thing with the capacitor, by the way. Capacitor initially has no objection. Build as much charge as you want. But the more you put charges in it, the more it's going to oppose. The more, until it's fully charged, then it's going to allow no more current going through it. So it's going to be like an open circuit. So it's the opposite behavior. Does this make sense to you, Alex, and everybody else? So the inductor doesn't like to change the current. It doesn't mind current by itself. It has no problem with the current, as long as it's steady, as long as it's going constant. Now, if it changes, go up or down, it doesn't like that. It's going to oppose that. So initially, it had no current because the switch was open. Once you throw the switch in the on position, now the current tries to go through it. It doesn't like that. It will not allow that. Ultimately, it's going to give in, and it's going to start building current in it. Once the current becomes steady, at that point, it's basically saturated in terms of currents. It's not going to allow more current going through it. Okay, that's what we found last time. It has this exponential growth in it. So the current goes from 0 all the way to a limit, and that limit basically is the final current that is going to be reached. In other words, dI over dt becomes 0. Okay. So as I was saying, if you guys are going to major in electronics or electricity or something like that, you will be dealing with far more complicated circuits, and this will be a walk in the park in a sense. This is just an introduction to the circuits in here. Yes? Okay, so let me continue with this problem to see. There was, I think, a couple more questions in it. Sometimes it freezes on me like this one. Find the reading of each emitter, okay? So find the maximum charge on the capacitor. The maximum charge on the capacitor, now we know the voltage, 16 volt. 16 volt now is in here. It's in actually here too, although it's open circuit, but there is a 16 volt in here because this entire point is the same. This entire point in the circuit is the same point here. All of these points are identical in terms of the voltage. And they are identical with these points. Now they are identical by themselves. All of these points are the same. This is, by the way, is not identical with them because there is a resistor in there. So there is a 16 volt in here between this point and this point. It's also 16 volts between this point and this point. And it's the same 16 volts between this point and this point. And there is no other device in here other than the capacitor. So I can find the charge now. Q over C is equal to 16 volt. That's the voltage in there. I know what C is. Did they give us C? C is 12 microfarads. It's given in here. And I know 16. So it's going to be 12 times 16 microcoulombs. So whatever 12 times 16 is going to end up being. How much is that? 12 times 16. 192 microcoulombs. Okay. Okay, so that's the answer to that question. It's easy because I know the voltage now. It's 16 volts, and I know the capacitance C. Although it's an open circuit, that's why it's not allowing, because it reached its maximum. It has zero charge initially, and now it maxed at 192 microcoulombs with this 16 volts. So that's it. You cannot put no more charges in it. Okay. You cannot put more charges. That's the maximum charge you're going to put in it. Draw a qualitative graph of the reading of voltmeter V2 as a function of time. V2 is the voltmeter in here. So as a function of time, remember initially, it had basically no current in it. I'd rather draw the current in there. Okay, I know that this question is a little bit weird, so I'm going to draw the current instead. And if I'm going to do this one, by the way, this is every thing we do in class is also required for your next exam. So this is the time. So this is the current now. Remember, initially I said there is no current. Okay, and at the end there is no current, but in between them there is a current. So it must have reached the maximum in here of some sort. Okay. It's going to reach it steadily in here. It's not going to, it's going to be a limit in here. So there is a maximum current that theoretically, if I do the time dependent solution, I can find it. So the behavior is not like what we did earlier. I'm sorry, is this the, this is di over dt, which is the voltage actually, okay? Di over dt, which is the voltage actually. So the di over dt is actually going to grow and then is going to come down to zero, okay? The voltage in this case, okay? So I think most of the times the analysis of the circuits has to do, if we're going to find the solution, we can find it theoretically, okay? And we should be able to get all of the answers that we have in there. The point in here is you have to understand what happened to the inductor, what happened to the capacitor, and they are actually the reverse problems in terms of the circuits. Okay. You have the homework already for chapter 30, and as a matter of fact for chapter 31, which did not even start yet. But I'm hoping to get that stuff done as soon as possible because it's going to be due as soon as we meet next time in after Thanksgiving. So here is the ideas for chapter 31. What is the, yeah, it's the same notes in here. And let's go to 31. So the stuff that we're supposed to cover is, first of all, the Phasors method. I know I mentioned it in the lab quickly, but we're going to get into a little bit more details in it. There is two different, what is the other one? The guy's name, I forgot the name of the person who invented the complex method numbers. Okay, I'll try to remember it and email it to you or send it to you guys. So you need to know at least one of these two techniques. You need to know the Phasors method or complex numbers method. Did you do any in Physics 4A? Did you do the phasors? Because I think it's in your book too, in Physics 4A. Does anybody remember this, the Phasors method, when you were doing waves, oscillations, and things like that? Does it ring a bell? Okay, so it's fine. And usually, again, we're not going to delve in it too much, okay, honestly, because we will have only one circuit, the RLC circuit in this class. And when you go, again, if you're going to be in majoring in any kind of engineering, it doesn't matter, even mechanical engineering, because you deal with oscillations a lot too, you're going to deal with this. You're going to find, sometimes they don't even tell you, they go straight out to one of them. Okay, the instructor will go straight into the complex numbers, for example, if that's his forte. If not, they will go straight to the Phasors method, okay? Because there is no way that you're going to spend pages and pages and pages with trig functions, basically, okay? To do the same thing, that is going to probably require only half a page with either of these two methods, okay? So that is the advantage of it, instead of dealing with the sine and cosine functions, which are very nasty and complicated when you're dealing with this, and you have to remember all of these identities and moving where the phase all of this. So what you do in this case, you use the Phasors method, which is just a geographical method, basically using geometry, or using the complex numbers, which is actually as powerful and as strong as the other one. And this works with all of the problems that deal with basically so-called linear problems with waves and oscillations and things like that. The minute we talk about power, and we're going to deal with power, both of them fail miserably. They cannot actually work. They are not going to work. Neither the Phasors method nor the complex numbers method, because both of them are for linear problems only. Nonlinear problems, you have to pull your sleeves and get back into the trig functions. There is no other way. You have to get the sine and the cosine involved. So that is basically what the idea behind this whole thing is. So that is really the first point. So we're going to get into the Phasors method, as it is. Why is my screen sometimes go blank? Okay, so we're going to do the Phasors method, and I'm going to probably allude to the idea also of complex numbers, because I prefer it personally more than the Phasors method, because the Phasors method really requires some sort of a ruler and pencil and basically paper, and you're drawing it to find where the angles are and all of these things. Complex numbers is totally does ignore that. It's pure algebraic method, and it's a very powerful technique too. Okay. Then we're going to define what the reactants are, and that is actually this is actually useful for complex numbers more than actually the Phasors method, but it's the same thing. Then we're going to go through the LRC circuit. Here is where I'm going to start. I'm going to start from this point, okay, and build the method here and go back into the idea first in there. Okay, so that's the more natural way to start, because we will find that we have a very hard problem to solve, okay? So what we do in this case, we use a geometrical method to work around it and find the solution, okay? Or we introduce, since the problem is very hard to do, we're going to introduce another hard problem to do, so we'll be facing with two difficult problems to do, but combining them, making them into a complex number, becomes an easy problem to solve. So that's basically the promise of complex numbers, and also the promise of Phasors method, okay? Now we're going to talk about power. At that point, these things fail. You have to go back into the trig functions, okay? And we're going to talk about basically about the LHC circuit. All of this is just about the LHC circuit, and finally we're going to talk about the transformers. I think we talked about them before, but we're going to just revisit and what they do and all of that. Okay, so this is the entire chapter. So here is the whole circuit that we're going to focus on for the entire chapter. In problems, I think there is 1 or 2 problems at the end of the book that deal with an LHC circuit, but not in this configuration. What I'm going to draw in this case is I'm going to draw the whole circuit in series, because that's basically what the book is, what the whole chapter is. So I have an inductor, I have a resistor, I have a capacitor, okay? And I have now not a DC power source, but an AC power source. Usually, for good measure, we have a switch in here, because we want to control the problem. So we want to throw the switch on at t equal to 0. And at t equal to 0, I'm requiring that there is no current at t equal to 0, that is, okay? And I'm requiring also there was no charge. This is not the most general problem that you're going to have. This is, if you wish, a restrictive problem, okay? Here is the problem with this whole thing. This circuit could have had the charge already to begin with in the capacitor, and or could have had a current running through it. And the problem becomes very complicated. It doesn't matter really if it had it or did not have charges, because what we're going to do in here, we're going to focus on the steady state. What that means is, when we focus on the steady state, these initial conditions do not matter. Because they will not impact the steady state, they will impact the transient. The initial conditions impact the transient only. So let me explain what we're doing then. We have an AC power source, like the plug of the house, okay? That is an AC power source, okay? You have an inductor L that doesn't like the current to change in its ends. You have a resistor, doesn't care which way the current is going to consume power at the rate of Ri squared. There is a capacitor that basically will build charge in it. Whichever way you put current in it, it's going to build charge one way or the other, okay? So after I turn on the switch, okay, then I wait a long time. I don't care about the transient. There is a behavior initially that is going to deal with the transient. I'm going to wait until the circuit comes to a steady state. Basically, how is it impacted by the source? That is basically the focus. So the source in this case is going to be V naught cosine of omega t. Okay, so it's a circuit. I mean, it's a power source that is oscillating between V naught and negative V naught in a sine function, in a sine way, in a trig function, in a harmonic fashion. Okay, so in this case, the circuit will respond by having current running through it. This current may or may not be in phase with the power source. As a matter of fact, I'm going to require that this current would be some maximum value times a cosine also of some omega t plus some phase shift. My problem is to find this I naught and this phase shift. That is the whole issue, okay? Because omega is the same omega as a power source. So we focus on the steady state by assuming, and we're going to verify this assumption, assuming that the current, which is sometimes called response, is proportional to the voltage V0, which is called the excitation. Okay, and has the same frequency, but may be shifted. Okay, in other words, I need to find I0 that I'm going to think that it must be proportional to V0. Because if I kill the power source, if I kill the current, maybe the circuit will go through transient again, which is always the case, but then it's going to go to zero. There will be no current. Case in point, for example, the light bulb is off right now. If I plug it in the wall, it's going to come back on. Okay? If I unplug it from the wall, it's going to go off. So my assumption in here, the current that is running through it, because of the excitation, must be proportional to the voltage that I apply through it. If the voltage is very high, it's going to run super bright. If the voltage is very dim, very low, it's going to run very dim. So that is my point in here. So that is the response need to be proportional to the excitation. So this is my response. And this is the excitation. Okay? And between this and that, there is always a transient. The transient may take a long time for the steady state to be established, or may happen right away. Most of the circuits that we have in our households, the transient is very short-lived, okay? But it's there nonetheless. And it's there when you turn on the circuit, and it's there when you turn it off. It's always there, okay? The system has to go through it, okay? No matter what. Usually inside the transformers, there are all kinds of protections that build chargers and things like that to counterbalance it. And it's really a headache in terms of your safety, okay? Because it can damage the electronics. The transient, although we're going to not focus on it, it can be disastrous. So you really have to deal with it as an engineer, okay? So that is one thing. The other thing that I'm assuming in here, the omega is the same, okay? Because ultimately this is the response, and it's taking its time to go back and forth. So the response I'm going to assume also is going to. Now, they may be in phase. They may max in the same time and go back into zero in the same time, or maybe there is a delay in the response, or actually the response could be ahead of the excitation. So that is what the phi is. Phi is the delay or advancement in the response. So again, we're looking for, there is a theorem actually in your calculus class for those who are taking, anyone is taking DFQ or took DFQ already? No? Well, if you take it, and I think usually it happens after the first 2 or 3 courses that you guys take, I think that it requires those calc courses. There is a theorem actually in calculus that basically states that a second-order differential equation of this type, which is going to be a second-order differential equation, non-homogeneous, will have 2 solutions. There's the transient solution, and they don't call it the transient solution. They call it the solution that depends on the initial conditions, or it has 2 constants actually in it, and those 2 constants can only be determined with the 2 initial conditions that we have, the current and the voltage. And a special solution, they call it. What that means is a special solution, any solution you find, as long as there is another solution, okay? So the hunt usually for the special solution depends on the excitation. You would want that special solution to be exactly proportional in intensity to the excitation, and you would want it to also have the same frequency as the excitation. But you don't necessarily have to have it in phase with it, because again, there is a transient that may delay things or actually push things ahead. So the transient actually the one that messes up for you things. Okay, so that is basically how the circuit is. And usually when you're doing DFQ, like I said, you're going to come back to this example, as a matter of fact, that we're doing in physics, to understand what you're doing in math, and also to use a mechanical systems also in the case of systems there, like we did in physics 4A, to understand also what's going on. And the focus then also is going to be on transients, okay? Because believe it or not, once not on transients, I'm sorry, on the steady state, because transients really make things very, very hard mathematically, okay? The algebra will become a little bit cumbersome, okay? I'm still in this page in here. So we're going to apply Kurkov's rule now. So we're going to take a point, just similar to what we're doing in there. So we're going to take this point, starting point, start. Usually we start from the switch, but it's fine. And we're starting immediately after it. So there is a voltage drop now on negative LDI over dt, I'm sorry. So Kurkov's rules, negative LDI over dt, plus the voltage drop across the resistor, which is going to be actually another drop, so it's going to be negative. Going to be minus Ri, minus another drop in the inductor, in the capacitor, Q over C, plus now voltage that is going to, I'm going to write it exactly the way that it was written, V naught cosine omega t is equal to 0. Okay? So this is basically the entire thing. This is simple as that. Now, moving things into one side will make all of this negative signs positive, and we'll leave this guy positive. So what we'll have in this case is, okay, let me make the point that the rate at which the current is building up, the charge is building up actually in the capacitor is given by this expression. So di over dt simply becomes d second of q over dt, second. So now the equation becomes L times the second derivative of q with respect to time, plus r times I, which is dq over dt, plus q over c is equal to the voltage times cosine of omega t, okay? Usually, we don't like it this way. Sorry, did I say, it's the same thing, okay? I'm gonna make a switch because I don't like that negative sign. Do you guys mind? Signal in here, I'm going to make it a sign. And in this case, the signal in here is going to be a sign. Does anybody object on this thing in here? So I'm changing just the power source. The reason why, because if I continue with the cosine, I will have a negative sign, which is going to cancel, which is fine. Everything is going to be all right. But I really don't like that negative sign from the get-go. So I'm assuming the power source is a sign, okay? The reason why is because I'm going to take the derivative of everything in here and deal with the current instead. Okay? If you like the cosine, just add a 90 degree to it and you're fine, okay? If you don't like what I did, the cosine actually is a sine shifted by 90 degrees. So you'll have everything plus 90 degrees everywhere. It's the same thing, okay? And now then, you don't have to deal with that negative sign. So, having said that, this will become just sine of omega t. Everything else stays the same. Okay? Now, if I take the derivative of everything, so the expression then I have for this expression in here is going to be the third derivative of the current, which is the charge, which is just the derivative, the second derivative of the current now with respect to time, plus r, the second derivative of q with respect to time is just di over dt. And now when I take the derivative of q, is just the current over c. And this is equal to v naught omega cosine now of omega t, because when I take the derivative of a sine, it's going to be a cosine. Okay. Or we could have solved it in terms of the charge. It's the same thing, okay? So I'm assuming the current now has this form, I naught times the sine of omega t plus phi. So this is my current I. That means that di over dt will be equal to I naught times omega times a cosine of omega t plus phi. And what else do we need? The second derivative, d second of I, with respect to time, is going to be minus omega squared I naught times a sine of omega t plus phi. Okay? here is what's going on. The voltage across the resistor, R, is proportional to the current. So the voltage will have no phase shift as far as the current is concerned. So it's going to stay sine omega t plus phi. So it's going to have the same phase as the current. So V sub R, the voltage across, how many C's in across? 2 C's? I think, I don't know. Maybe I have too many. The resistor is in phase with the current, meaning whatever the phase of the current is, it's omega t plus phi. The voltage across it is going to be just a number, R times I. So you just scale the amplitude of the current. Instead of being I naught, you multiply it by R. So it's going to be either, if I have 100 ohms and the current is 1 amps, so instead of 1 amps, it's going to be 100 volt. That's all. So you scale the amplitude. That's all. The phase stays the same. So if it was a cosine, it stays a cosine. If it's a sine, it stays a sine. So the voltage across the resistor stays the same. However, the voltage across the inductor, okay, will have to deal with L times the second derivative now. I'm sorry, L times the derivative of I, I'm sorry. So the voltage across the inductor L is L times di over dt. And that is L omega times I naught times a cosine of omega t plus phi. So when you take the derivative now of the sine, it becomes a cosine. I'm going to make this cosine back to sine because I don't like it. But now, not because of the assumptions, using trig. So using trig. So I know sine of omega t plus phi, and if I add to it 90 degrees, that is the same thing as, I'm sorry, yeah, the same thing as sine of omega t plus phi times cosine of 90 degrees plus cosine of omega t plus phi times the sine of 90 degrees. Again, this is an identity from trig. This is 0, this is 1. So the cosine that I have it in here can be written as a sine, but shifted by 90 degrees in the positive direction. So the voltage across the inductor is ahead by pi over 2 versus the current, because I can write VL as the same thing as L omega times I naught. In other words, I'm going to scale its amplitude too, but instead of scaling it by a single number, I'm going to multiply it by omega and L times the same sine that I had for the current. Remember, the current is a sine, okay, of omega t plus phi, except that it has a 90 degree in it, 90 degree angle added to it. So for some reason, the voltage across the inductor is shifted upward by 90 degree angle, by positive 90 degree angle, as you can clearly see from this expression. So far, the current, the voltage in the resistor is in phase with the current. And it's actually the amplitude is actually scaled by R. The amplitude in this case is scaled by omega times L, but it's actually shifted by 90 degrees. So it's ahead of the current by 90 degrees. So I say in this case, the voltage in the inductor is ahead by 90 degrees versus the current. It's ahead of the current, actually. It's leading the current. That's actually leading it. The word used in here is lead, not led, leading it. Okay? I'm going to do the same thing for the capacitor. For the capacitor, the voltage across the capacitor is the charge over C. And the charge is the integral of the current. Remember, the current is this expression, so I have to integrate it. So I have 1 over C, sorry, what is this? 1 over C, the integral of I naught sine of omega t plus phi dt. What is the integral of a sine? You guys know from your calculus? What is the integral of a sine? Minus cos. Very good. Thank you, Faraz. So it's a minus cos. But don't forget I have to pull the 1 over omega 2 because otherwise I will be in trouble. So I have to pull this 1 over omega because this is the integral over dt, so I need to do a change of variable to omega t, pulling the omega down. So this expression will become 1 over omega times c times I naught, which is a constant, and the integral of a sine is, as you duly noted, it's a minus cosine of omega t plus phi. Okay, so that is exactly what it is. Now, again, I don't like this business of a minus cosine. I want the amplitude to be by itself. The amplitude in this case is divide the amplitude of the current by omega c. So another way, scale the current by dividing it by fixed number, which is the frequency of the signal times the angular frequency times the capacitance C. Okay, so this takes care of that. But the entire minus also is a problem. If I leave it in here, I have something that I cannot deal with. So I have to replace this minus. So there is an identity again in trig functions that says the sine of omega t plus phi, if I subtract from it a pi over 2 or 90 degrees, is the same thing as the sine of omega t plus phi times the cosine of 90 degrees minus cosine of omega t plus phi times the sine of pi over 2. Well, a sine of pi over 2 is exactly what I need, is 90 degrees. This is 0. So this whole thing is actually the minus cosine. This whole thing in here is just the minus cosine of omega t plus phi. So I got rid of both the minus and I brought it to the sine the way I want it. So I want this one to be a sine, and I did get it into a sine. Here is the sine, okay? Exactly how I want it. Because the current happened to be a sine, so I want everything to be exactly matching the current. I don't care about the phase. We're going to talk about the phase. But at this point, we have it matching beautifully. There is nothing in front of the sine, no positive sign, everything is positive, everything is beautiful. So we know the amplitude of the voltage across the capacitor is also scaled by a factor of 1 over omega c. And it's shifted by negative 90 degrees, so it's lagging in this case, okay? So I say in this case, the voltage in the capacitor lags behind, basically. It's not ahead, okay? Lags by 90 degrees, okay? So that is basically the whole idea in here. That is actually the whole essence in here on how to make the circuit work for you in terms of phasors. If we started with a cosine, we'll have a minus cosine in here, but the algebra will be the same, believe me, okay? As a matter of fact, you can test it yourself. Remember when I made that switch in here, and I was kind of, because I would have to deal with another negative sign, and I would have to have another, but it's the same result, okay? So if the voltage was actually a cosine, not a sine the way I have it in here, this would be a cosine, and then everything would work the same, okay? Would be identical, except that there will be a little bit of complication in terms of getting the minus sign, but at the end the result doesn't matter. So here is the idea of the phasors then method. The Phasors method says the following: draw the voltage across the resistor, because it's going to be in phase with the current no matter where. Okay? Because it's always in phase. The voltage across the resistor is going to be in phase. So if the current is up, the resistor, the voltage across the resistor is going to be up. It may be scaled up or down. The amplitude may be more or less, because this is one thing measured in a voltmeter, the other one is measured in a current, in amps. But that's the only thing that you have to worry about, is the scaling. They go up and down in the same time, okay? Now the inductor is ahead, actually, is leading the current by 90 degrees. The capacitor is actually lagging by 90 degrees. So having said that, then the Phasors method says the following. Draw a vector in the x-axis whose amplitude is just Ri naught. Okay? Period. End of story. In the y-axis, leading, draw omega times L times I naught. Okay? In the y-axis also, so this is a 90 degree, positive 90 degrees in here. In a negative 90 degrees, draw your I naught over omega c. Find the sum of these two numbers. These three vectors, basically. You have to have three vectors to add them. So in this case, I add this vector, which is a negative vector with that one. So probably the answer is somewhere in here. So this is the difference between omega L minus 1 over omega c times I naught. Okay? By the way, I naught now, I can ignore it because it's the same thing happening in here, happening in here, happening in here, happening everywhere. So for right now, I'm not going to even worry about the amplitude of omega naught. So when we're doing the Phasors method, we don't even worry about I naught at all. We worry just about the numbers R, omega L, and 1 over omega c. That's it. Okay? So think of this one as the difference between omega L and 1 over omega c. It could be here, it could be here, it could be 0. So you have three possibilities. This difference could be positive, or actually, if 1 over omega c is bigger than omega L, it could be negative, or it could be actually 0, where everything cancels in terms of this 2, and the only thing that remains is just R. So in this case, if I draw it in here, and if I happen to have the algebra here, then this, when I add these two vectors together, this is the vector that I'm going to have in here. The amplitude of this vector is what I call z, which is just the square root Pythagorean theorem of the adjacent to this angle. This is phi, by the way. I'm sorry. This is the, yeah, this is the phi, the angle that I'm going to look for. So in this case, it's going to be what? Let me try to find it in here. So it's going to be r squared plus this difference squared plus omega L minus 1 over omega c squared. And the tangent of this phi is simply omega L minus 1 over omega c divided by r, the opposite over the adjacent. Okay? And now, basically, this is the whole essence of the Phasors method. Okay? That is how we basically solve the circuits in here in the with the phasors. So this is the Phasors method. So the first thing you draw is R by itself, and then you have to, as a matter of fact, we have names for these things. Omega times L is called XL. This is the reactance of the inductor. The reason why we call it reactance is because it looks like it's a resistance. As a matter of fact, it has the same units as the resistance of the inductor. Just think about it. L times di over dt is the di over dt is a voltage. Okay, is the voltage across a resistor. So the units for L are the same units of the amps of the current, which is I, divided by second. Okay, so the inductor L has the same units of L, has the same units as a voltage times second divided by a current. And the current is an amp. So this one, volt over an amp, is actually an ohm. So this is an ohm times a second. Okay? So an inductor has the ohm times a second, and omega is 1 over second. That's an angular frequency. Omega has the units of 1 over second. So when you multiply L times omega, the units for that is an ohm times a second divided by a second, so it's actually an ohm. Because from this expression, L di over dt, L times an amp divided by a second is a volt. So if you multiply both of them by the amp, you will have a volt divided by an amp. That's Ohm's law. V equals to Ri, by the way. So if this is a volt and this is an amp, the unit of V over A is actually an ohm. Okay, so the unit V over A is an ohm times a second, but omega, which is the radians per second, is the angular frequency, and it's 1 over second, so we multiply L times omega, it's an ohm. So the inductance now is actually like a resistance. It has the same units as the resistance, but this is coming from the inductor. Same thing with 1 over omega C. Let's think about that. 1 over omega C is actually XC. This is the reactance of the capacitor. And it too has the same units as an ohm. Let's check why is that. Remember, Q over C is a voltage. So the units of the Q divided by the units of the capacitance are actually a voltage. And the Q, which is the charge, is nothing but an amp times a second. Remember, the current is the rate of charge per, which is di over dt. I mean, dq over dt is I, is A. dq over dt is A. So Q by itself is A times dt, which is amp times second, divided by a coulomb. Okay, so this whole idea then gives me one of capacitance. So the units of the capacitance, 1 over capacitance, is the same thing as a voltage divided by this amp, and again divided by second now, because you bring the second to the other side, it's going to be in the denominator, because the second and the amp come together. So this is an ohm. So the same thing in here, this is an ohm divided by second. But if I divide by a second now, divide by an omega now, so 1 over omega times C, the units for that guy is the same as an ohm divided by second, because that's the units of 1 over C, times the units, or divided by the units of the frequency, and the units of the frequency are themselves the inverse of a second. So the units of omega is 1 over second. So basically you will have an ohm over second times 1 over second. The second cancels the second, and you have an ohm. So indeed, this is also an ohm too. So this acts like a resistance also. So both of them in this expression, they have the same value as omega times L, which is XL, and 1 over omega C, which is XC, are actually like ohms. And this is an ohm minus an ohm divided by an ohm. It's a number. The tangent better be a number, because the tangent is a dimensionless number. Okay, so everything matches in terms of the units. Everything works fine. So in this case, Z, which I'm going to call the impedance of the circuit, which is equal to the square root of R squared plus XL minus XC squared. This too is an ohm too, because this guy is an ohm squared, and this is an ohm minus ohm, which is an ohm squared, which is an ohm squared. Ohm squared plus ohm squared is an ohm squared, and the square root is going to be an ohm. So Z also is an ohm. Everybody is an ohm now. XL is an ohm, R is an ohm, XC is an ohm, and Z also is an ohm. So everything is an ohm at this point, okay? So except the phase now, which is the arc tangent, arc 10 of XL minus XC over R. This could be positive, this could be negative, okay? So this whole thing could be positive, could be negative, and the algebra then becomes as follows. The solution to the circuit becomes as follows. So first of all, the current I is going to be I naught, which is simply V naught. I'm sorry, I naught by itself, not the entire expression. V naught divided by Z times the cosine of omega t plus arc 10 of XL minus XC over R, this whole thing, okay? So in other words, the current I naught is equal to V naught over the square root of R squared plus XL minus XC squared. As we duly noted in the beginning, what time is it, 1:50? As we have noted in the beginning, the intensity of the current better be proportional to V naught, and it is. So if I kill V naught, if I kill the current, if I kill the voltage, I naught will be 0. So the response now is indeed proportional. The intensity of the response, not the actual response. The intensity of the response proportional to the excitation V naught, as we expected. The phase, though, here is the phase. Okay, it has to do with the, how far off XL minus XC are. Okay, so basically this whole thing then can help us solve these problems, and this is basically where the heart of the Phasors method is. Okay, can give you both the phase and the amplitude too. Now, in terms of this current, let's rewrite it in terms of the frequencies now. So I naught, the response, is equal to V naught divided by the square root of R squared plus omega L minus 1 over omega C squared. When omega is super small, this term is 0, and this term dominates. So the expression in this case will give you a current that looks like this. I naught equals to roughly, I'm taking the limits now, of V naught over the square root of R squared plus, this is negligible because omega is super small. 1 over omega becomes big. When you square it, the negative becomes positive. So it's going to be 1 over omega, the whole thing squared. Okay? And this term is still much bigger than R squared. So this whole term then becomes V naught over 1 over omega C. Okay? For very small frequencies. As a matter of fact, this will be 0 because omega will go all the way upstairs in here. So I naught will be very small for low frequencies. How about high frequencies? For low frequencies, the response is negligible. How about high frequencies? How about when omega goes to infinity? So let me rewrite the expression again. So I naught is equal to V naught under the square root of R squared plus omega L minus 1 over omega C squared. Now we're taking omega super large. Okay? When omega is super large, what happened in this case, this term becomes 0. 1 over a huge number is 0. This will dominate the expression. The inductor will dominate. Okay? So in this case, I naught will be simply equal to V naught over square root of R squared. This is the limit, of course. We're taking the approximation now. Omega L squared now. Well, omega is still large, so this term will dominate still. So V naught will be 1 over omega L. The square root, this is 0 now, negligible in front of omega L. So when you have, what happened in this case, 1 over omega becomes very tiny, and then the response also is very negligible. So the response is negligible for high frequencies. So it's very small for low frequencies, it's very small for high frequencies. The capacitor wins for low frequencies. The circuit is more capacitive. As a matter of fact, the phase now I can find it. When omega is very small, I can find the phase, and it's going to be dominated by the negative 1 over omega C. So it's going to be a negative phase. Okay. For high frequencies, it's going to be dominated with the omega L because 1 over omega C will be 0, negligible. So again, in this case, actually the response will be ahead. Okay, because like an inductor does. Somewhere in between them, there is a maximum. So this is how the current looks like. So this is the current now, I naught, the intensity of the current, as a function of frequency. Somewhere in here is 0, somewhere in here at infinity is 0. So it's going to peak somewhere in here. I need to find the peak in here. Where is it going to peak? So for that, this function, by the way, I naught is equal to V naught over a square root of R squared plus omega L. This is omega, okay? Minus 1 over omega C, the whole thing squared. So this is the function that I really need to examine to find the different stuff for it. Normally what we do in this case, we multiply it by omega everywhere in the numerator and the denominator, and that should take care of a lot of things. So this expression becomes I naught becomes V naught times omega divided by the square root of R squared omega squared plus L omega squared minus 1 over C. Okay, as a matter of fact, there is another simplification that I could do in this case and actually get the LC also out, okay? And if I do that, this expression, okay, I'm going to define something in here to do the algebra a little easier, okay? So 1 over LC is what we defined before, way back, as omega naught squared, okay? I think on Monday we did that, okay? And having said that, then what we're going to do in here, we're going to take the L out. We're going to take the, when we take the L out, I will be left with omega C squared. No, it's squared in here, I'm sorry. Okay. And I will have an R over L in here. So let me do this algebra quickly in here. So I naught will become V naught times omega times this. When I take L from here, it's going to come out as L squared because of this square. And I'm going to take it out completely. So I'll have to divide by it again in here. So it's going to be square root of R squared over L squared. And then I have it in here too, okay? Omega squared plus omega squared minus omega naught squared, and the whole thing is squared. If you guys think that this is too fast, please let me know, okay? It's just basically trying to reshuffle things in here in terms of the algebra. R squared over L squared is what I defined also before, if you guys remember, as 2B, okay? So 2B was R over L, okay? That's what we did on Monday, okay? So the expression then looks like this. I naught is equal to V naught over L times omega over the square root of 4B squared, omega squared plus omega squared minus omega naught squared, and the whole thing squared. This is in terms of the terms that we defined a long time ago. The reason why I like it this way is because now we can take the derivatives, okay? As a matter of fact, there is another simplification. We could take omega naught squared in here out, so it's going to be omega over omega naught, and then I have an omega naught squared in here, and then we're going to have it in here again, and the expression, instead of taking the derivative with respect to omega, we're going to take the derivative with respect to omega over omega naught. Here is the task for the day. Find di naught over d sub omega, okay, and equate it to 0. The reason why you want to find this expression, you want to find where it reaches its maximum, where this function is at its peak, okay? And then find the maximum. You will find that the maximum, so basically we have to take the derivative of this expression with respect to omega, okay? That's going to be some function of omega. Then take this f of omega and make it equal to 0. Obviously, it's going to vanish also at infinity too, okay? Because this approaches infinity in a symptotic fashion, but we don't care about that. We care only about the resonance, where it's going to peak, okay? So we're going to find that it's going to peak near omega naught, not exactly omega naught. So this point in here, maybe omega naught is here. It's going to be shifted by an amount that depends on R, okay? So we're going to find where it's going to be, where omega naught is, that what I defined to be just 1 over square root of LC, by the way, okay? So we're going to find it where it's going to the derivative vanish, and we're going to find exactly where that maximum is, okay? And from there, we're going to find the resonance, basically exactly what's going to happen. It's going to happen around omega naught. At that point, the phase, or I think it's going to be exactly omega. I don't know. I'll have to do it myself too, because it's been a long time since I didn't do this algebra. You're just taking the derivative. Okay, if you guys don't know how to do it. So you guys remember what the task was today? So you have this function, okay, which is gives you the voltage, I mean the current, is as a function of omega naught, as a function of omega, and you're supposed to take its derivative, this expression. And if you don't like this one and you prefer to work with this one, it's the same thing. What is it? The original expression. It's this one. Okay. Find where it maxes. Okay, so we're going to take its derivative and do the manipulation and equate it to 0. There are some websites you just put the function, it's going to give you the derivative. Okay, if you guys are good with math and Mathematica, you can do it theoretically there too, or with okay, so let me give it to you guys so to give you time to copy it. Okay, the last expression is this one, but I can give you also the starting expression, because this one has additional symbols that we used. But let me give you the initial one, okay, that we started with. So I naught is equal to V naught divided by the square root of R squared plus omega L minus 1 over omega C squared. This is not the end of the story, though. The end of the story is going to be actually finding also phi, which is the arctan of omega L minus 1 over omega C divided by R. Okay, this you don't find its maximum, because let me graph that second function. This is how it looks like. This is 90 degrees, and this is negative 90 degrees. Okay, initially, it's going to be for low frequencies, it's going to be dominated by the capacitor. For the high frequencies, it's going to be dominated by the inductor. So this function would look like this. The transition now depends on R. For low R, it looks like that. For high R, it looks like this. This is R very large. This is R very small. Okay, so it's going to be in phase at omega equal to omega naught, and it's going to be out of phase by 90 degrees actually for low frequencies. Again, this is omega, by the way, and this is phi. Okay, by 90 degrees, by negative 90 degrees for low frequencies, because it's dominated by the capacitor, and here it's dominated by the inductor. I think there were some questions in the lab about these things. And also, this is how the frequency would, this is how the current would look like. So you can work with this expression. You don't have to work with the other one. So you have I naught equal to V naught divided by the square root of R squared plus omega L minus 1 over omega C, both of them squared, under the square root. And you're supposed to find where it maxes. Ignoring infinity, okay? And I think also omega equal to 0 also is going to be an extrema, okay? It's going to be minimum. So you just find it where it maxes, because we know it maxes. It's 0 both ways, so it has to be somewhere which is a positive value. It's always positive. The square root is positive. V naught is positive. So in this case, it's positive somewhere. So it has to go through a maximum. We need to find that maximum. Did everybody write this expression? We have 1 minute left. Yes? Okay, at least one person did. I'm hoping the other guys too have a chance to go through this, because this is pure mathematics, has nothing to do with physics. okay? But then the applications of this are tremendous in physics because resonance has a lot of applications, okay? One of them actually is the lab, but you're going to do a lot of resonance. So we're going to talk about this one when we meet back on Monday, the 30th of November. Okay? And we're going to continue this discussion with chapter 31 because we're most of that done, except that I want to do this whole thing with complex numbers, and you will see it's similar to it, but it's going to be fun. Then we're going to do the power, okay, and talk about the power because it doesn't matter in physics or anything unless you do the energy, because that's when it matters, that's when it costs you money. And we're done with this chapter, and we get into the last chapter where we solve Maxwell's equations and basically find Poynting vector and all of that. The exam most likely is going to be on December 9th. That is the 4th exam, and the final is going to be the Monday after. Exam 4 is December 9th. So we have time, I guess, to work out these things. And I'm hoping to finish grading your class because we just have had an exam. And some of you still have some issues that I need to fix with them, and I'm hoping to have the grades ready this Thanksgiving break. Okay, I think we went a minute up more than the time allotted, so I can stop the recording now.